Hello everybody. Today I'll be presenting our work Asterisk Super Fast MPC with a Friend. This is a joint work by Banasri Karmakar, Nishat Poti, Arpita Patra, Shikhar Patnavis and Divya Ravi. Let me start with an example where a set of clients want to avail some service which is for which they send their private information to the centralized service provider who computes the required function and sends the output back to all the respective parties. However, performing computation in this way is not secure, as the private information of all the clients will be known to the centralized service provider, as well as various data protection law may prohibit such services. So therefore, the system is broken. A solution to the above problem is by multi-party computation, in short MPC, for which a set of mutually distrusting parties can compute a function jointly on their private inputs. For that, they may need to interact among each other for a few rounds. The security guarantees that an MPC protocol provides are correctness, which says that the output of the protocol is indeed correct, and second is privacy, that says if a party is corrupt, if it is adversarial, then it cannot learn anything beyond the output of the functionality. In the literature, there are various MPC protocols, but depending on the security guarantees that they provide, it can be categorized primarily into three categories. I'll describe them from the weakest to the strongest. The weakest one is security with abort, where an adversary can choose to abort a protocol. It can prevent honest parties from learning the output. However, it can learn the output. A slightly stronger notion is called fairness, which says an adversary can still choose to abort a protocol, but if the adversary prevents the honest parties from learning the output, it cannot learn the output either. That is, either all the parties obtain the output or no one does. And the strongest guarantee is guaranteed output delivery, in short GOD, that says, irrespective of the correct party strategy, all the honest parties always get the output. Depending on the adversary's power, that how many parties it can corrupt, the mainly protocols can be classified into two classes. First is honest majority, where the security and privacy guarantees of the MPC protocol are preserved only when the number of corrupt party is less than half of the participating party. On the other hand, there is a class of protocols which is called dishonest majority protocol. Usually honest majority protocols are more efficient and it can give a stronger security guarantees of fairness and GOD. However, the number of corrupt parties it can withstand is much lesser in comparison to dishonest majority protocol. Whereas dishonest majority protocols can withstand all but one corrupt parties, but at the cost of the computational cost is higher and as well as the communication is also more. Also, from the literature, it is known that in this setting, it is impossible to achieve the stronger security guarantee of fairness and GOD. Therefore, both the models have certain good and bad aspects. What we want to breach the gaps and achieve the best feature of both these models, and for that we consider an alternate model. And in that alternate model, we introduce the central party of the insecure computation as a helper node into the MPC computation. However, we want to achieve privacy even against that helper party. For that purpose, we consider it as semi-honest. This model is more suitable for scenarios like where there exists a centralized governing entity whose job is to maintain the integrity of the system. For example, dark pool, where Securities and Exchange Commission can enact the role of the helper party. So, what is the dark pool? We will come to it later in the presentation. And in this model, we can achieve the best feature of both honest majority and dishonest majority protocols, that is higher resilience, better efficiency, and also computationally much more lightweight, as this is symmetric based crypto. Okay, in contrast to the standard MPC where there exists only one adversary, here multiple adversaries exist, that is one semi-honest helper party and a malicious adversary corrupting majority of the party. Depending upon the relation between these two adversaries, there are few scenarios that we need to consider. First is that simultaneous and colluding, that the helper party is helper party and the malicious adversary, they exist simultaneously and they are colluding. A prior work proved that even in this model it is impossible to achieve fairness and GOD security guarantee. We consider slightly weaker model where they exist simultaneously, however they are not colluding, though the malicious adversary can send non-protocol messages to the helper party. In this work we prove even in this weaker model it is impossible to achieve fairness and GOT guarantees. Finally, we are left with the model where either the helper party is semi-honest or malicious adversary corrupting majority of the parties. In this model, it is possible to achieve stronger security guarantees of fairness and GOD. The protocol will be efficient, it is as efficient as honest majority, and it does not rely on any cryptographic hardness assumption. Okay, I'll summarize the result of this work now. First, we have an impossibility proof that I discussed in the earlier slide. Formally, it says that if the malicious adversary corrupts majority of the parties and the helper is semi-honest and they exist simultaneously, although they are non-colluding, but the malicious adversary may send non-protocol messages, that is its complete view, to the helper party, then even in this model, it is impossible to achieve fairness and guaranteed output delivery guarantees. Then we consider the model of either or, where either the helper party is semi-honest or majority of the parties are malicious. In this model, we are able to achieve a stronger security guarantee of fairness for any generic n, and we demonstrate our construction is extremely efficient and even it is scalable with the number of parties by implementing it. Finally, we consider a suitable application for this model, dark pool. For that, we build the required primitives and we implement them and benchmark it. We compare our construction with the state-of-the-art honest majority and dishonest majority constructions with its asymptotic cost. In comparison to dishonest majority protocol, we are able to improve the security guarantee from abort to fairness while improving the pre-processing communication cost by at least a factor of n. And when we compare it with honest majority protocols, we were able to improve the security guarantee resiliency from honest majority to close to dishonest majority without incurring any additional cost. In fact, in terms of total cost, our work is slightly better than MP clan, where it requires 3n elements in total, whereas our requires 2n plus 3 elements. For give a better understanding of the performance, we compare with the dishonest majority work in the pre-processing phase, and we ran it for up to 100 parties. Even for 100 parties, the state-of-the-art assisted MPC protocol has significantly higher runtime as well as communication. Here observe that both this communication and the runtime, the y-axis in the logarithmic scale, so in the runtime the gap may not seem significant, but the time difference is much more than what it represented from the visual data. Okay. For 5 parties, we compare with the other dishonest majority protocols of mascot, overdrive, and assisted MPC. In terms of communication, we improve mascot. We have an improvement over mascot by a factor of 352 times. Over overdrive, it is 306 times, and over assisted MPC, it is close to 7 times. And in terms of throughput, which is the number of multiplication triple can be generated in unit time, we have an improvement of 288 times in comparison to mascot. And over overdrive, we are able to achieve an improvement of 228 times, and over assisted MPC it is close to 3 times. We compare our online phase with honest majority and dishonest majority works where they are implemented on a popular MP speeds framework. We see a slightly high runtime in our case, and this is due to the optimization in the implementation in the MP speeds framework. However, in terms of communication, we can see our work outperforms both dishonest majority as well as honest majority construction of Atlas. We consider the application of dark pool, where a list of buyer and a list of seller um, exist, and the seller wants to sell some unit of goods or stocks, and they give a preferred price, selling price for those stocks. This and also a list of buyers, they want to purchase some stock. For that, they submit their preferred bids and how many units that they want to buy. These requests are sent to a centralized entity called Securities and Exchange Commission, who obliviously perform a matching between these buyers and sellers. and uh, all this matching happens privately. Why it is important to perform this matching privately? It is extremely important to keep all this information, that how many units are getting bought or sold or at what price. These informations are extremely sensitive. Otherwise, for a company, if an information like let's say x many stocks are getting sold, are getting public before the transaction happens, that can have significant impact on the market, and the company stock may fall suddenly. Therefore, until the transactions happen, this information should remain private. However, in the current solution, the problem is that it has a single point failure. Therefore, we consider two popular algorithms to solve this problem. One is continuous double auction, where a stream of buy and sell requests are there, and whenever a new request comes, then the algorithm tries to find the best suitable match. And this continuous double auction is more suitable in the server outsource setting, whereas another matching algorithm exists that is called volume matching, which processes buy and sell requests in epochs where all the parties can take part into the computation. For continuous double auction, we run it in the server outset setting with uh, 5 parties, and we consider buy list and sell list size from 500 buy list and 500 sell list, and we see that the time it takes to match this 1000 request is close to 16 seconds, and the total amount of communication is required is less than 1.8 MB. We execute the volume matching algorithm with 50 buyers and 50 sellers, all of them taking part into the MPC protocol, and the time it takes is less than 2 minutes to match 50 buyers and 50 sellers, and the total amount of communication is less than 2.5 MB. Okay, now we'll go into a bit of technical construction of our protocol. Any computation of any function can be represented in the form of arithmetic circuit. That is, it consists of a few addition and multiplication gates. The evaluation happens in the following way. First, the inputs are secret shared. Then, on the secret shared input, addition and multiplication gates are performed, followed by, corresponding to the output gate, we perform the output reconstruction. Since the computation happens on the secret shared data, we will discuss first the secret sharing semantic that we use in this work. First, we use additive secret sharing, where a secret X is split into n components, where each of the components individually look random. And we want and we use additive secret sharing primarily because here among the n participating parties, all but one parties can be corrupt. In fact, they can be malicious, and that is why we use authenticated additive sharing, where a secret X is authenticated, and for that we use information theoretic MAC, where delta is the global key and TX is the corresponding tag, which is delta times X. The authenticated sharing contains additive sharing of the secret X, additive sharing of the global key delta, and additive sharing of the tag TX. Our protocol is designed in the pre-processing and online paradigm, and therefore we use a different authenticated secret sharing, that is what we refer to as masked secret sharing, where the secret is first split into two components, masked value and random mask. Throughout the computation, we maintain the invariant that a secret X is split into two components, masked value, which is prepared in the online phase, and the mask, whose authenticated sharing is generated in the pre-processing phase. So a masked secret sharing of a secret comprises of a masked value, which is available to all the parties, and a random mask is authenticated shared. And the authenticated share of the mask consists of additive sharing of the mask, additive sharing of the global key, and additive sharing of the tag. For the input gate, consider P be the dealer. In the what we want to achieve masked secret sharing of the input V. In the pre-processing, a random mask delta V is prepared and its authenticated sharing is shared with all the parties. Then helper party sends the mask delta V to the input provider dealer PD. In the online phase, PD computes MV, which is V plus delta V, and sends it to all the parties. Here, out of everything, only it is left to discuss how to generate the authenticated sharing of a random value delta V. Input addition gates are pretty straightforward. Since the secret sharing that we use are linear in nature, therefore non-interactively parties can perform the sharing, obtain the sharing of the additive value. Slightly tricky thing is multiplication gate. Consider x and y are the inputs of a multiplication gate and z be the output, which is x times y. X and y are masked secret shared among the parties. We want to obtain masked secret sharing of the value z. In the pre-processing, the mask of z, that is delta z, would be prepared and it would be authenticated shared. In the online phase, we want to generate masked z. Note that masked z must satisfy this relation where all the other information are available from mask shading of x and mask shading of y. The things that is not available are delta xy and delta z. So in the pre-processing, first delta xy, that is delta x delta y, and delta z are prepared by the helper party. Then parties obtain the authenticated shading of delta xy and delta z. In the online phase, pi computes authenticated shading of masked z by performing this equation, and then the peaking, and then they send it to one party p1 who performs the reconstruction and sends mz to all the parties. Only thing here left is to discuss how this sharing is generated. Final thing is output reconstruction, for which all the parties have the masked value, but they have only authenticated sharing of the mask. They do not have the mask in clear. Before obtaining the mask in clear, it is important to check all the intermediate reconstruction of the masked value is correct or not. For that purpose, all the parties, including helper party, perform a match check. The helper party obtains either 0 or 1, and if it is 1, then it gives delta V the mask to all the parties, otherwise it gives the bot. If the parties obtain the delta V, then they can compute the output, otherwise all of them abort. So everyone obtains the output or no one does. That's how we obtain fairness. So we will skip the max check part, which is done by performing a random linear combination on the secret shared value. Now the thing that is left is to discuss how to generate this authenticated sharing. Note that helper party has the knowledge of V as well as global key delta. It can compute the tag TV. Then it can sample the shares corresponding to P1 to P2, P1, P2, Pn, and sends the shares to each of the parties. So in total, this requires 2n elements of communication. We optimize it by using common key setup, where P1, where Pi and the helper party has a common key Ki, and using a PRF, then P1 to Pi, P1 to Pn minus 1 non-interactively sample their shares of V and TV. Finally, helper party computes Vn and Tvn corresponding to Pn and sends it to Pn. So this requires a communication of 2n MB. So we are able to improve communication from 2n to 2. Okay. So I'll end my talk with following few questions. First is that in this model, that is either the helper party is semi-honest or the malicious adversary corrupts majority of the party, we are able to obtain security guarantee of fairness. Enhancing the security guarantee to GOD is not that difficult, because if the protocol aborts, that means the malicious adversary corrupting some parties, and hence the helper party must be honest, and then the computation can be completed by sending out all the private information to the helper party, who can compute the required function, and sends it back. However, this nullifies the whole purpose of the MPC. So the challenging question is to obtain the GOD without relying on the helper party. And a follow-up question of this work would be to use this framework and obtain secure computation for PPML and federated cloud computation. With this, I'll conclude my talk. Thank you.